Okay, so through the miracle of modern technology, so like Keaton is gone today, so yes, Keaton, I'm doing this for you. If you're gone, I've got my own YouTube channel, not sound grandiose, but it's a necessary evil. And so what I'll do is I'll record the lecture and then I'll upload it to YouTube and then I'll send you that link. So if you're ever gone, that's what'll happen. It's handy if you email me, because in that way I remember, because anymore I have like the memory of a goldfish. So if you're gonna be gone, email me and say, hey, Burkamp, please record the lectures, and then I will get that to you. Because that way it's gonna be easier than just missing it. That I have to reteach it, so it's actually, it works out well for you and it works out well for me. So that's the story. All right, so let's chit chat about those conversions. So don't forget, you're going to have a pretty simple quiz tomorrow on anything complex over like density, writing stuff in scientific notation, conversions, that type of thing, okay? So nothing horribly complex, all right? But probably be like maybe one page, something like that. So not a huge deal. All right, so before I get started, does anybody have any specific ones that you want me to work?
Yeah.
Yes?
Okay, so I eventually figured it out, but just so that you can like really show me clearly, can we go over 3? Number 3.
With the ethanol?
Yeah.
Okay, yeah. All right, so here's the basic idea of number 3. So start with the idea that density is mass divided by volume. Start with that idea, okay? So if you look in terms of, sometimes it's handy to develop what's called an algorithm, okay? An algorithm is just thought process, and you do that before you actually start putting down the numbers. Because what I found is that kids get so wrapped up in, what equation am I going to use, okay? And you get wrapped up in the equation, and then you lose track of the big picture, okay? So at the end of the day, you look at this and say, hey, what's the volume? All right, so right away, I know what I have. I've got a density, okay? And I'm given a mass. So at some point, I know I have to find a volume. Okay, so first thing I've got to do is I have to solve that equation for volume. Okay, now, I'm old school. I like solving variables for variables first, because that's how science is done. Okay, if you read scientific journals, everything is done with variables. Okay, you never see numbers. So on upper level science, that's what you have to get used to. Okay, you have to get out of the kind of this algebra 1 mindset that says, oh, I'm going to put in numbers and then I'm going to solve for it, okay? So if you get in this mindset that says, hey, I'm going to solve the equation first, and the sooner you kind of embrace that idea, the deeper that understanding is going to be. All right, so what does this look like solved for volume? Volume is going to equal what? Mass divided by density. Okay, there you go. So now, when I get this, that volume, if you look at the units, that volume is going to be in cubic centimeters. So the answer, though, asks for liters. So then I know I'm going to have to do another step where I change that into liters. So here's the 2 things that I know I'm going to have to do. I'm going to have to take the mass and divide it by density to get a volume. But I know that volume is going to be in cubic centimeters. And then I'm going to have to take those cubic centimeters and change that into liters, okay? Now, it's also handy if you can visualize, hey, is this going to be a big number or a small number, okay? You have 50 kilograms. 50 kilograms is like 100 pounds, okay, roughly. So you got like 100 pounds of ethanol. That's going to be a lot. So I got to figure that, wow, this answer is going to be pretty big. And so that's a situation where you want to think through it and go, 50 kilograms, 100 pounds, that's a lot of ethanol, okay? Because if you think about like water, okay, if you have 100 pounds of water, that's a lot of water, okay? So I got to figure that my answer is going to be a pretty big number. Now, here's the worst thing that you can do, is just randomly start writing down numbers without the units, because that's just going to be an absolute train wreck, okay? So let's tackle this. So I got volume, right? So I got 50 kilograms, right? Fairly high degree of precision, 50.0, okay? So my density, though, is in 0.789 grams per cubic centimeter. So if you do this wrong, here's what you do. You just take this 50 and you don't realize that it's in kilograms, you just write down 50. And then you divide that by 0.789 and then you get an answer and it's like, oh, a miracle happened and here's my mass, okay? There's a huge difference between 50 kilograms and 50 grams, okay? 50 grams is like 50 paper clips. 50 kilograms is 100 pounds, okay? Kind of a big difference between the two, okay? So what am I going to have to do with those 50 kilograms? Izzy, what am I going to have to do?
Convert it into,
Convert it into what?
grams.
Okay, so what's the conversion between kilograms and grams?
Okay, so there's 1,000 grams in 1 kilogram.
This, you speak words of truth,
Okay.
okay? All right, so my kilograms will cancel out, right? So I take 50 times 1,000, check my math, but I should get 50,000. So I get 50,000 grams divided by 0.789 grams per cubic centimeter, okay? And again, pay attention to the units. So these grams are going to cancel out. The cubic centimeter is in the denominator of the denominator, so it flips up. Cool, I get cubic centimeters. So you do that, that's going to get you a number. It's a pretty big number, okay? Like 63,000 and some change, okay? But so that answer is going to be a pretty big number, 63,000, But that's in cubic centimeters. So now, what are you going to have to do with the cubic centimeters?
Convert it to liters.
Convert that into liters. And what's the conversion between liters and cubic centimeters?
There's 1,000 cubic centimeters in a liter.
Yeah. So there's 1,000 cubic centimeters in 1 liter. My cubic centimeters cancel out. You get liters. So your answer to number 3 should be in the mid-60s. Okay? Got a ballpark of where you should end up. On number 5, okay? So let's talk about number 5. There's a couple of different ways you can work number 5. So, because we're going to deal with percentages a lot. Number 5, and I don't care how you do this. If you like proportions, you can say, oh, remember, percentage means out of 100. So if you like percentages, you can go, okay, hey, that's 3.5% sodium chloride, otherwise known as salt. So that means I got 3.5 grams of salt per 100 grams of water. And now what I'm saying is that I got 325 grams of salt water, and that's X number of grams of salt. So take 3.5 times 325, divide by 100. So if you like proportions, set it up as a proportion. Okay? It's cool, it works. If you go, oh, Mr. Burkamp, I like to multiply percentages. Oh, good for you. Okay? So percentage means out of 100. So the other thing that you can do is 3.5% as a decimal, right? Is 0.035, and you can just take 0.035 times 325, okay? You can do that. You can take 3.5 times 325 and divide by 100. It's all the same math. But here's what you want to think through. You know your answer to number 5 has to be less than 325, because 325 is the whole thing, right? So, I want to find what mass is out of that 325. So if you get an answer on number 5 bigger than 325, it doesn't make any sense. It's like, I only have 325 grams, but I'm going to have 400 grams of salt in that. It's like, think that through, okay? I can't have more grams of salt than I have of salt water, okay? Nature doesn't give extra credit. It isn't like, oh, test, what'd you get on the test? Oh, I got 110 out of 100. I got extra credit, okay? Mother Nature doesn't give extra credit. So you know your answer has to be less than 325. Now, the converse of that is number 6, okay? So And this is how this plays out. So if you ever, bless you, if you ever seen, sometimes they'll advertise like, oh, natural sea salt. Okay, so literally what they'll do is they'll take sea salt, they'll spread it out over these big areas, they'll let the water evaporate, and then they'll scrape up the salt from it. Okay, that's one way to get, you let the water evaporate and the salt's left behind. Okay, so there's a couple of ways you can work number 6, but think this through. So number 6, I want to end up with 87 grams of sodium chloride. So I know I have to start with more than 87 grams to end up with that. So I know my answer has to be bigger than 87. Okay? Because I can't start with less salt water than 87 and still get 87. It doesn't make any sense. So that's where his hand is like, just start with the idea of what your answer should be before you even start the math. Like, all right, it's got to be bigger than 87. That's cool. Okay. So again, there's a couple of ways you can work number 6. One option is that if you like ratios, okay, which is cool. So you start with that same idea that says, oh, this is 3.5 grams per 100. Okay. Now the thing with this is on number 6, you say, I want 87 grams of sodium chloride, and that's going to be X number of grams of water. Okay? If you like ratios, and this is how I work the problem. I set it up as a ratio. I like ratios. So I said, okay, 3.5 over 100 is going to equal 87 over X. Take 100 times 87 and divide by 3.5. Okay? There you go. So if you like ratios, you can do that. Now, if you like percentages is a little bit sketchier. Because basically what you're saying on that one, you're going to say, I'm going to take 0.035 times X number of grams of water is going to equal 87. Okay? So this one's more of an algebra problem. So this one you're saying, I got to take 0.035 times some number so I can get to 87. Oh, I'm going to get X by itself. I'm going to divide both sides by 0.035. So at the end of the day, you do the exact same math. The only thing you change is kind of the conceptual idea, and you change the sequence. So if you do the proportion one, okay, basically, you're going to take 87 times 100, and then you're going to divide that by 3.5. So with this one, you're going to take 87, and then you're going to divide that by 0.035, because this has already been divided by 100. You do the exact same math, it's just however you want to approach the problem. Okay? Cool with that one. So your answer to number 6 should be between 2,000 and 3,000 grams. Now, how can you check that your answer is right on number 6? How could you work backwards and see if you got the right answer? Yes?
Divide 87 by the number that you got and see if it's
Yeah.
around
Take the 87, divide it by the total mass, see if you get 3.5%. Okay? There you go. If you did, you did it right. If you didn't, it's a train wreck. Okay? There you go. All of your answers on number 7 should be around 1,000. Okay? All of those should be around 1,000. On that back side, and I want to make sure everybody's cool, for example, on 2A. So on 2A, this is how I want 2A work. So you got 4 liters per 1 hour. Okay? That's what that means. So this would be like, let's say, for example, you're up in Canada, and they tap into the maple trees and they get maple syrup out of the trees. Okay? Well, here's the flow rate. You get 4 liters per hour. A liter is like a gallon. Okay? So there's roughly 4 liters in a gallon. So what we're saying is that this tree or this pipeline or whatever it is has a flow rate of basically a gallon an hour. That's not very much. Okay? You're only getting a gallon an hour. Imagine that you're filling up your car and the pump only dispenses a gallon of gas per hour. Okay? It's like, wow, I come through there all day just to fill up my car. Okay? Thankfully, gasoline comes out a lot faster than maple syrup does. So I got 4 liters per hour, okay? I want to change that into, in this case, milliliters per second. So I've got to do 2 things. I got to change the liters into milliliters, and I got to change the hours into seconds, right? Okay. Which one do you want to do first?
Yeah.
The hours? Okay. So I'm going to put 1 hour up here, and then I'm going to put 3,600 seconds down here. So if I just do this step, what units do I have? If I just do this step, what do I have?
The seconds.
Well, I've got liters per second,
Yeah.
right? So if I just do this step, the hours have canceled out, I have liters per second. If I just do this step, that's the units that I have. It's liters per second, okay? But I don't want liters per second, I want
Milliliters.
liters. So now, how am I gonna tackle the liters? Carter, what am I gonna do? How?
Multiply by 1,000.
Fantastic. So 1 liter is 1,000 milliliters. The liters cancel out. Miracle happens. I get milliliters per second. So I'm going to take, just like Carter said, basically that's going to be 4,000, and then I'm going to divide that by 3,600. Okay? There you go. Yes?
Okay, so I get like the right answers, but I don't fully understand like the proportions thing. So you're gonna count me out for not doing it in that way?
Here will be, no, not necessarily.
Okay.
But here's the issue that I'm gonna have, okay? Is that if your answer is wrong, God forbid, I've got to be able to work backwards and see what you've done. And so if you'll still show me like the cancellations, that's cool. But if you just have random numbers written over there, and I can't follow that, that's gonna be a train wreck. And again, the sooner that you embrace this idea, because we're gonna use this for mole conversions, we're gonna use it in stoichiometry, we're gonna use this all the time. And keep in mind, I've been doing this longer than you've even thought about being on this earth, and literally, you look at my answer keys, this is exactly how I work these problems. You know why I work in this way?
Easiest?
It's the fastest and most efficient way to do it. So literally, you look at, I work all these problems. This is exactly how I work every one of these problems. And if there's a better way to do it, I teach you that. Okay? All right, so your answer on that back side on number 2, the first answer should be around 1, and the answer to 2B should be around 7. Okay? All right. Anything else you want me to go over? Anything at all? Oh, seriously, Jayhawk, what?
Maybe like 7B.
7B?
Yeah.
The sheet of aluminum foil? Yeah, no
Yeah.
worries. Okay. So here's a sheet of aluminum foil, right? Pretty thin. True? Okay, y'all seen aluminum foil. So it's 165, so that's one dimension. And then by 23, there's the other one. And then it's got a thickness of 0.980 millimeters, right? So at the end of the day, I'm going to take density as mass divided by volume. My mass is going to be density times volume, right? Cool with this. Now, all of these densities are grams per cubic centimeter, which means that volume has to be in cubic centimeters. Okay? You see that? But here's the problem. I was a jerk when I typed this up. Because I gave you centimeters, and millimeters. So the 2 centimeters are cool. I got to change the millimeters into centimeters. Now that's pretty simple. Okay, I got 0.980 millimeters. How many millimeters are there in a centimeter? 10. So there's 10 millimeters in 1 centimeter. So take 0.98, divide that by 10. then there's that volume. So then then you're just gonna multiply all three of these numbers together, multiply it by the density.
Okay,
Good?
yeah,
Great?
yeah, I think so.
Okay, fantastic. Anything else? Going once. Going twice.
Wait,
Should have done it faster. What?
C,
On which one?
7.
Okay. You have the volume, right? What units of volume in?
Cubic centimeters?
Okay? I've given you the density of water, 0.998 grams per cubic centimeter. That's the easiest one. Because you don't have to do anything. You have the density in grams per cubic centimeter. You have the volume that's already in cubic centimeters. You're handicapped because you're wearing KU stuff, I understand. I'll take pity on your soul.
Oh,
If you were wearing a K-State shirt, you would have seen that right
I
away.
wore a K-State shirt the other day.
And you did much better. Look what happened when you wore KU stuff. I swear to God. Don't ever wear KU stuff on test day. You are cursed. I'm telling you that right now. Okay. Yes?
Would 4B be used or no?
Would 4B?
Yeah.
No.
Oh, I just wonder if there's like a big enough difference.
Oh, yeah. Because if it's completely sealed, if there's any change at all, it won't
Oh,
hold.
okay.
Okay, anything else? I'm gonna try to get that handed in.
Sorry.
Thank you.
All right, so here's where we're at kind of in our journey, okay? So the first thing we gotta do is kind of, and I start the same way with like my physics classes as well, kind of what I call the toolbox, all right? So we've got to figure out basically how do we do chemistry? What tools do we need to do chemistry, okay? We got the concept of density. We know how to do conversions, okay? We've talked about the basic structure of the atom. Protons and neutrons are in the nucleus. Electrons are around the outside, okay? So now we kind of get an idea of this is what we have to be able to do to move forward in terms of the analysis, okay? So it's like, the analogy is like you want to work on your car. You know that the alternator, which recharges your batteries, is out, okay? If you know that, that's fine. But if you don't have the tools to swap out the alternator and replace it with another one, knowing that the alternator is out doesn't do you any good. Okay, so you got to have the tools. So the same thing is going to happen with chemistry. So to do chemistry, you have to have a certain tools kit. Okay, how do you do conversions? What are we going to measure stuff in? How do we use the periodic table? What's the structure of the atom? Now that we have that, now we can actually begin to build on that structure. So one of the most important things about chemistry is that it's very specific in terms of its terminology. So this is on this lecture notes that I just gave you, okay? So let's start at the beginning. If something's an element, okay? If something's an element, what that means is that, by the way, get out this periodic table. So, if something is an element, what that means is that first and foremost, you can find it on the periodic table. So, you can kind of make the analogy, if you're familiar with the concept of Legos, which I'm guessing you all are. So, what the periodic table tells us is the different types of Lego blocks that we have to build a universe, okay? That's it. That's what it tells you. These are the types of Lego blocks. And then how you assemble those Lego blocks, you can get a binder clip, you can get clear plastic, you can get a penguin, you can get an Oreo cookie, okay? You can get Alk grill, okay? So how you reassemble those Lego blocks determines what you get. And certain Lego blocks will hook up together and other Lego blocks won't. So like the noble gases, those Lego blocks, they don't connect with other Lego blocks, okay? Because they're like cool, they don't need to, okay? You want to mix salt, sodium chloride. Oh, that's sodium. You have a sodium Lego block and you have a chlorine Lego block. And those hook up together because they want to join up, okay? So, and chemistry is basically the study of either how you assemble the Lego blocks or what happens when we exchange Lego blocks. So the lab that you're going to do today is just like an observation lab. And we want to introduce some different things. So if it's an element, you can find it on the periodic table. So for example, you can't find water on the periodic table. The reason that you can't find water on the periodic table is because we can take water and we can separate it into its two constituent parts of hydrogen and oxygen. So if I can take water, for example, I can break that up into hydrogen and oxygen gas. And later on, you'll see the significance of these two. Okay, they're called diatomics. Okay, but for now, just accept that I can separate this. But what I can't do is that I can't take hydrogen and oxygen and break that apart any further. Okay? So when you hit the point that you have an element, what that means is that you cannot break that down any further. Okay? That's it. So you notice like milk. Milk is not on the periodic table. It's an important part of life, don't get me wrong. Okay? But you're not going to find milk on the periodic table because milk is composed of a whole bunch of different things. Right? So basically, if you talk about these elements, these cannot be broken down any further and still be stable. Okay? So the Greeks had a cool analogy. If you look at the word atom, it actually goes back to ancient Greece and those philosophers. So a quick history lesson. Okay, world history, here you go. Okay. So if you look at the ancient Greeks, there's kind of three big philosophers. Aristotle, Socrates, and Plato. Okay? And so Socrates taught Plato, Plato taught Aristotle. So it kind of goes in that sequence. And the Greek word, the atom, actually comes from the word that means indivisible. So how they viewed the universe, or this concept of an atom, is that imagine that this is a chunk of pure gold. Okay? Chunk of pure gold. And I have this really, really sharp knife. And I'm going to take that knife and I'm going to cut this thing in half. Okay? All right, I'll cut this half in half. It's still gold. So then I'm going to take that half, I'm going to cut that half. And if you think about where that knife is going to go, that knife is going to go in the gap in between these particles. Okay? That's where it's going to go. It's going to go in that gap. It's like if I'm trying to hand out papers, I'm not going to try and walk through the tables. Okay? I'm going to walk in the gap between the tables. So that's where that knife is going to go. That knife is going to go in that gap between these particles. And what they visualized, they said, okay, we're going to keep cutting and cutting and cutting and cutting and cutting. And at some point, we're going to get this little tiny particle that we can't cut anymore. Okay, so in other words, when we get to that last tiny bit of matter that still has the properties of gold, but yet we can't cut it with the knife, that's how they viewed the atom. Okay? Now, they had no concept of protons, electrons, neutrons, anything like that. And literally, if I was teaching this class like 100 years ago, if you look at the history of science, if I was teaching you all 100 years ago, I would not give a lecture about electrons, protons, and neutrons. Really hadn't found them yet. Okay? So this whole concept of subatomic particles is, in the scheme of science, is pretty new. Okay? So here's a short version. We'll talk more about this later. So something's an element. You can find it on the periodic table. Now, the next big thing is what we call compounds. Okay? So a compound is Lego blocks connected together. Okay? So one way you can kind of visualize this, and we'll use this a lot. This is a molecular model kit. So, and you've got like different colored little spheres, okay? Like this is oxygen, that's nitrogen, hydrogen. So if I want to make a compound, let's say I want to make water. Okay, so I'm going to take an oxygen, okay? And I'm going to put that here, and then I'm going to put hydrogen on the end, and put another one. Voila, I have made water, okay? So this is how we represent water. Now, it makes it look like it's static, like the hydrogens aren't moving, the oxygen is anchored here, and then it's locked together by a physical bond, okay? That isn't how it works. But this is a good way of visualizing it. So this is a compound. It's made up of elements of hydrogen and oxygen. So these are like the Lego blocks. So I've got a Lego block that we call oxygen, and I've got Lego blocks that I call hydrogen. And if I combine those together, I get a compound of water. So basically, what chemistry studies is, number one, what's the structure of water? What does it look like? Is it bent like this? Is it straight? What does it look like? So you could also build, for example, I don't know, let me see. You can build ammonia, okay? Which is kind of cool. That's what very distinctive odors, okay? So if you build ammonia, which is NH3, then that has a completely different structural look than water does. So ammonia, which is NH3, okay? So that's one nitrogen, Lego, that's the little blue one in the middle. And then you've got 3 hydrogens attached to it. So this looks completely different than the water molecule does. But these are both compounds. So basically what chemistry tries to figure out is that, can these react? Can water react with ammonia? Okay? If it does, what do we get out of it? If it doesn't react, why doesn't it react? And what can we do to make it react? Okay? So, those are compounds. The next thing we'll talk about is what we call mixtures. So something's a mixture that's composed of either different types of elements or different types of compounds, or maybe it's an element with a compound. So when you have mixtures, there's 2 broad classifications. What we call homogeneous and heterogeneous. So if it's homogeneous, that means everything is in the same phase. So when you talk about phase is a fancy word for what's the structure like. Is it a gas? Is it a solid? Is it a liquid? Those are going to be the 3 big things that we're going to talk about. So you can have gases, you can have solids, you can have liquids. So let's say, for example, I take some sand and I pour it into the water, into a beaker of water. Okay, that would be a heterogeneous mixture because I have solid sand mixing with liquid water. Okay, there you go. Now, the air that you breathe, which is kind of important, okay, we have an atmosphere, which is a cool thing. Without this atmosphere, we wouldn't be here having this discussion. So air is a homogeneous mixture because it's got nitrogen, mostly nitrogen, some oxygen in it, okay? A little bit of water vapor, some other weird things, a little carbon dioxide, okay? Increasing levels of carbon dioxide. So air is a homogeneous mixture because it's all that. Now, yesterday, we talked when we mixed like the cold water and the hot water, okay, that would be technically a homogeneous mixture. We mixed, it was all water, okay, but we just mixed it based upon temperature. But even when I took the food coloring and I added that to it, that food coloring dissolved in the water, so that's what made that a homogeneous mixture. So if you can basically look at it and say, hey, there's two different types of phases in here, that's a heterogeneous. If it's all one phase, whether it's all liquids, all solids, whatever. So this room as a whole, is this room as a system, is this room heterogeneous or homogeneous? What'd you say?
Heterogeneous.
Why?
Both, there's gas like in the air and there's solids.
Yeah, okay. And we can throw some water on the tables and then we have the liquid phase too. Okay? Right? So yeah, we all live in a heterogeneous mixture. Okay? So that's the first thing you gotta keep straight. So you have elements, you can find it on the periodic table, that's an element. If you can combine those elements, that's gonna be a compound. And then we can talk about mixtures. So the lab you've got, that's gonna be some of the questions that you're gonna do. So in the lab, you're gonna roll around and you're gonna look at different types of reactions. Some are pretty simple, some are more complex, okay? So, one of the things you're gonna be asked to find on the lab is gonna relate to some different properties. So on this periodic table, down here at this bottom left, there's some information that you need. Basically, it's the key. What is this information giving you? So what you're gonna need to know for this lab is there's a number here that says the melting point, okay? So the melting point is that transition from a solid into a liquid. It's a phase change because you're going from a solid into a liquid. So, like for example, what they have with zinc down here in the bottom, so the melting point of zinc is 420 degrees Celsius, okay, 419.23. So what that means is that if you're below that melting point, and this is going to be important, so if you look at zinc, and that's actually one of the metals that you're going to deal with. So if you look at zinc, we usually shorten melting point to MP, that way we don't have to write the whole thing out. So the melting point of zinc is 420 degrees Celsius. So what that means is if your temperature is above 420, that means it's going to be a liquid, okay? If you're below 420, that's going to be a solid, okay? So think about water. What's the melting temperature of water in Celsius? 0, okay? So if the temperature is below 0, you have ice. If the temperature is above 0, you have liquid water, okay? Now, let's think about the gases. We have two primary gases that make up our atmosphere, oxygen and nitrogen, okay? So then you talk about the boiling point, okay? So the boiling point is where you go from a liquid into a gas. So for example, what's the boiling point of water? 100 degrees Celsius. So we're right now at about 20 degrees Celsius. So we're in between the melting point and the boiling point, so this is why water is liquid. Oxygen and nitrogen are all gases. So what that means is that those at room temperature are existing as gases. So that means that we're above that boiling point because they're at a gas, okay? So when you look at zinc, all right, zinc has a melting point of 420. Right now we're at about 20 degrees Celsius. So we're well below that melting point, so that means this is why zinc is going to be a solid. So you're going to be in the lab and you're going to find this little bar of zinc. Oh, right, that's a solid because we're below the melting point. So the other thing that's going to be important is that you're going to need the number of protons, which is that atomic number. So for zinc, that's like 30. So in the top left-hand corner, when it says the atomic number just means the number of protons. Okay, you're all familiar with that concept. Okay, then what's going to be different is this number up here in the top right corner, 65.409. So let's talk about that number real quick. We'll spend a lot more time talking about this. Okay, and this is what we call the relative atomic mass, all right? I will spend an entire lecture explaining the history and the importance of this number. The thing with relative atomic mass is that it isn't a true measure of the mass of an atom. It's a relative scale, okay? So if you notice, hydrogen, okay, if you look at the relative atomic mass of hydrogen, that's 1.00. Carbon, 12.00. So here's a simple way to think about this. Relative atomic mass of hydrogen is 1. The relative atomic mass of carbon is 12. So what that means is that you would have, if you wanted to balance it, it would take you 12 hydrogen atoms on one side to balance out 1 carbon atom on the other, okay? So on a relative scale, it would take you 12 hydrogen atoms to balance out 1 carbon atom. If you look at magnesium, relative atomic mass of magnesium is like 24.3, okay? So what that means is that a magnesium atom is twice as massive as a carbon atom is. So relative atomic mass of carbon is 12, magnesium is 24.3. So what that means is that it would take you 2 carbon atoms to balance out 1 magnesium, okay? Relative atomic mass is one of the most important concepts that we will talk about, okay? So today I'm just laying out the groundwork for it, where it is on the periodic table. So what you're gonna do, you're gonna have 4 metals: iron, zinc, aluminum, and copper. What you're gonna need, and this is gonna be on a chart you're gonna fill out, you're gonna need to write down the atomic number, relative atomic mass, and then you're also going to need the density, okay? So on these densities, okay, so you've got zinc, that density, 7.14 grams per cubic centimeter. So you're gonna have 4 metals, and you're gonna have to fill out that information. So you just have to know how to use this to get that information, okay? Got it? Good, great. So stop that camera for a second.